Dropping a drill bit 2,000 meters into the ocean floor is one of the most expensive gambles in modern engineering. A simple deep water exploratory well costs between $125 million and $150 million, with specialized drill ships costing up to $800,000 a day just to lease. Historically, 8 out of 10 exploratory wells drilled in these frontier conditions come up completely dry. This immense financial and technical risk is why the Union Cabinet recently approved a massive 84,084 crore rupees central scheme titled Samudra Manthan, a name borrowed from ancient mythology that literally translates to the churning of the ocean to extract hidden treasures from the deep. If you look past the commodity headlines, there is a far more compelling technological reality taking place. This 84,000 plus crore rupees investment isn't just an energy policy. It is a state-funded push to construct an indigenous deep-sea hardware, robotics, and supercomputing ecosystem from scratch. The official Samudra Manthan announcement structures its 84,000 plus crore rupee outlay across 4 distinct operational pillars. First, the government is allocating 28,534 crore rupees for offshore data acquisition to fund modern 2D, 3D, and AI-driven seismic mapping across unexplored marine basins. To accelerate deep water exploration, a massive 43,200 crore rupees is earmarked as a 50% state risk share subsidy for drilling 60 exploratory wells capped at up to 65 crore rupees per well. Another 10,000 crore rupees is dedicated to building common offshore infrastructure hubs, allowing operators to share subsea production and evacuation facilities so smaller deepwater discoveries become commercially viable. Finally, the scheme sets aside 2,000 crore rupees to establish integrated oil and gas manufacturing and services zones, creating a localized supply chain under Make in India for specialized subsea hardware and marine services. The second and fourth pillars directly target a harsh physical reality. Operating at a water depth of 2,000 meters means confronting environmental physics at its absolute limit. Pressure hits roughly 200 times atmospheric levels at sea level. Ambient temperatures hover near freezing and total darkness prevails. Physical human intervention is completely impossible. Every piece of mechanical work on the ocean floor must be executed by world-class remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs. These multi-ton underwater robots act as the hands and eyes of engineers on the ocean floor. Equipped with powerful robotic arms and high-definition cameras, they install critical drilling equipment, inspect pipelines for damage, and even carry out repairs in an environment where no human diver can survive. Now, operating on the seabed is only half the engineering challenge. The other half takes place on the surface. When a drill ship lowers a steel riser pipe 2,000 meters down to touch the ocean bed, that ship cannot drift. If ocean currents or monsoon waves sway the vessels more than a few meters off center, the subsea pipe will bend, fatigue, and snap. To prevent this catastrophic failure, specialized deep-water vessels use Class 3 Dynamic Positioning Systems, DP3. A central computer constantly tracks the ship's position using satellite signals, underwater sensors, wind data, and other navigation systems. It then automatically adjusts powerful thrusters beneath the vessel to keep this massive ship almost perfectly stationary over a single spot on the ocean floor, without ever dropping an anchor. Today, India imports almost 100% of this subsea equipment. When an Indian operator attempts to explore deep water blocks, almost all the capital leaves the country to pay foreign equipment makers, specialized vessel owners, and international service giants. Now, this is why the 2,000 crore rupees manufacturing zone allocation and the 43,200 crore rupees drilling subsidy are critical. By sharing the financial risk of $150 million exploratory wells and building localized manufacturing hubs, the scheme aims to build an indigenous supply chain for subsea robotics and deep water engineering, finally breaking our total reliance on foreign equipment vendors. Okay, so why should anyone in tech care about an oil scheme? I know that's the question. Because deep sea exploration is no longer an oil and gas story. It is a massive supercomputing and algorithms problem. Before dropping a $150 million drill bit, you have to map what is 2 kilometers under the seabed. Survey vessels blast acoustic sound waves into the ocean floor and record the returning echoes. In the Bay of Bengal and Krishna Godavari basins, dense subsea salt structures and thick basalt layers distort those sound waves, turning raw survey data into uninterpretable static noise. To turn petabytes of distorted acoustic echo data into a clear 3D map, geophysicists must run reverse time migration (RTM), solving complex differential wave equations in reverse. This is one of the most computationally intense tasks in modern engineering, requiring weeks of continuous petaflop scale computing power. Historically, Indian exploration relied on black box, proprietary Western software suites like Schlumberger's Petrel or Omega. India spent millions in foreign licensing fees every year just to process data from its own seabed, creating a critical digital monopoly and a vulnerability to software lock-in. To reduce this dependence, CDAC Pune, along with ONGC's GeoPick and IIT Roorkee, developed SeisRTM under the National Supercomputing Mission. It's an indigenous seismic imaging software designed to run on Indian supercomputers like Param Siddhi AI, reducing India's reliance on expensive foreign software. This is why 28,534 crore rupees of the scheme is dedicated to offshore data acquisition, with 4,000 crore rupees set aside for AI-driven reprocessing. The Directorate General of Hydrocarbons (DGH) manages over 10 petabytes of legacy seismic data in the National Data Repository (NDR). Instead of spending hundreds of millions sailing survey ships back out to sea, AI inversion models and domestic supercomputing clusters will reanalyze this dark data to instantly reveal hidden deep water structures. Now, we must keep in mind that executing this tech shift unlocks a payoff that goes far beyond finding oil. Building custom wave equation solvers like SeisRTM and applying physics-informed AI models proves that Indian supercomputers can solve high-level geophysical math. Scaling this software stack enables domestic deep tech firms to export high-performance processing services to offshore energy markets across Asia, Africa, and the Middle East. Using AI to reanalyze 10 petabytes of old seismic data also creates a blueprint for unlocking dark data, the massive amounts of information organizations already have but haven't fully used. The same AI techniques could later be applied to everything from satellite imagery and weather forecasting to national mapping projects. Finally, the underlying data infrastructure built for this mission directly supports the broader blue economy. The precise subsea mapping and robotics telemetry developed here will feed directly into adjacent marine sectors, from laying submarine telecommunication cables to positioning offshore wind turbine foundations and conducting deep-sea mineral surveys. Now, turning this policy into actual flowing energy means navigating three hard operational realities. First, deep water exploration is pretty much a marathon. The industry benchmark from initial 3D seismic mapping to first commercial oil spans anywhere from 7 to 10 years. Even if exploratory wells drilled under the new subsidy discover reserves by 2028, actual commercial production will only materialize in the decade after 2031. Second, there is a global shortage of deep water infrastructure. Drilling 60 ultra-deep water wells requires specialized drill ships that can operate at depths of 2,000 meters. These vessels are in extremely high demand globally, with daily charter rates routinely topping $450,000 to $500,000. Securing enough ships within a tight 5-year window will push the procurement capabilities of DGH and ONGC to their limits. And finally, building a local supply chain takes time. While the 2,000 crore rupees manufacturing zone aims to localize subsea hardware under Make in India, certifying heavy equipment and autonomous robotics to withstand 200 atmospheres of undersea pressure involves years of rigorous testing before anything can go into production. So, obviously the road ahead is long, but the trajectory is clear. By treating the seabed as a high-tech frontier rather than just a fuel reserve, India is taking a massive leap toward true digital and industrial self-reliance. Ultimately, Samudra Manthan might look like an oil exploration scheme. But beneath the surface, it's really an attempt to build India's deep-sea robotics, supercomputing, and engineering ecosystem from scratch. If you enjoyed this deep dive that looked beyond the standard headlines, make sure to like and subscribe to Tech Brew with Vandana Nair. And I'll see you in the next one.